Good afternoon. My name is Julien Vanegue. Today I'm going to present our work about non-termination proving at scale, which is joint work with Azalea, Raad, and Peter O'Hearn. So why do we care about non-termination bugs? First of all, we all know that termination is an undecidable property. It's not possible to prove termination for every program in a general case. And not only that, but termination bugs in real programs, they're very pernicious. They're really hard to see because when you have a program that actually do not terminate, typically that program is not going to respond. And it's possible that you have, for example, a server where all of a sudden is not responding anymore to the request from the clients, and you're not going to see any crash. And that can lead to real problems, real security issues such as denial of service attacks. On top of that, in the last 20 plus years, we found more than 1,000 non-termination bugs were identified publicly and reported in the MITRE CVE database. And as we can see, the trend of those bugs is going up. And it affects all languages that are Turing complete. That's the case for C, C++, Java, but also for JavaScript, Rust, Go, and every other memory-safe language. So here we're talking about really a property that's going beyond memory safety. So let's talk about what we know already, the past, the correctness, and the over-approximation techniques that people have been using mostly to prove termination in the past. Obviously, correctness, as you all know, is proving the absence of bug. So for example, if you have a piece of code C and you start in a pre-state satisfying the precondition P, and you know that this piece of code terminates, then that will lead to a post-state that satisfies the post-condition. Proving this in the over-approximate setting will be guaranteeing you the absence of bug. However, you may have false positive because you may analyze spurious behaviors of the program. On the other hand, using incorrectness reasoning and under-approximation is meant to prove the presence of bugs. So it may be that you found a bunch of bugs, but also you will have no false positive by construction. So it's really useful to be able to put this in front of developers because those developers are really sensitive to noise. And as soon as you actually put a static analysis tool in front of them that has noise, then they're not going to like you. They're going to disable the tool. So it was very important to us to focus on a methodology that was no false positive by construction at the expense of false negatives. Just a few reminders about incorrectness logic. Incorrectness logic is a logic that was created by Peter O'Hearn, published at POPL 2020. And the semantic triples for incorrectness logic are as such. It's using the square bracket instead of the curly brackets as in whole logic. And on top of that has a tag, epsilon, in the post condition that can tag whether you are analyzing a normal execution, an execution that has no error, or an erroneous execution that is leading to an error state. For example, if you want to analyze this fragment of code x equal y, and you know that y equal v, then you know that in the post condition, x is equal to y is equal to v. On the other hand, if you hit an error in a piece of code that you're analyzing, and you started to execute this error in precondition p, you know that you're going to lead to an error state that also satisfies p. So one of the first contribution of the paper is that the realization that there are two kinds of under-approximation. The first is called forward under-approximation, and the other backwards under-approximation. And it turns out that those two under-approximation styles are equivalent. You can differentiate those two by their characterization lemma. At the top, you are quantifying over the post states. So for all s in the post, satisfying the post condition q, there exists a state s prime in p, such as s prime is linked to s by executing c, starting in p. So really, this corresponds to the existence of a path. On the other hand, you can also quantify on the pre-states and require that there is at least a post-state s prime in q, such as s and s prime are linked by executing c. This is also known as a Lisbon triple. So in under-approximate reasoning, you can use a bunch of standard rules. For example, you can use sequential composition on the right-hand side. If you have a piece of code C1 that starts in a precondition satisfying P and leads to a post-condition state satisfying R, And then you have another piece of code, C2, that starts in a pre-state that satisfies R and leads to a post-state satisfying Q. You can do a sequential composition of C1 and C2 to build C1, then C2, that goes from P to Q. In incorrectness logic, on top of that, you can use something called short-circuiting, where if you know that C1 starting in P goes to an error state satisfying Q, you know that any sequential composition, C1 compose C2, say, will also lead to a post-condition, error post-condition Q. You can also model branch in incorrectness logic. For example, you can have a choice operator where you can decide whether you want to actually go down the path of an if or the path of an else. And this is called path dropping. It's really useful to be able to scale to very large programs because you can focus on specific paths that you care about. In incorrectness logic, you also have rules to handle loops. For example, you may unroll many times a given loop, going from P to Q, or you may unroll 0 times if you never enter the loop, where P and executing C 0 times still lead to post-condition satisfying P. And that's really powerful as well because you can do a bounded loop analysis. So you can do basically k-bounded loop analysis where you can go down the path of a loop until a certain bound, and that avoids you to really get into infinite path of a given loop execution. These are great, but this doesn't handle termination or non-termination. In fact, incorrectness logic only handles finite traces. But one of the realizations is that while termination is a correctness property, non-termination is an incorrectness property. Indeed, if you look at the piece of code at the top, in order to know that if ren skip else x equal 1 terminates, you need to go down every path, and you need to know that the if part is going to terminate, as well as the else part is going to terminate, which is the case in our small program fragment here. If you want to prove non-termination on a program, for example, the below code, if ren skip, do nothing, else, while true skip, diverge, then you only need to prove that one path of the program is actually non-terminating, which is why non-termination is inherently an incorrectness question. So we built a new logic based on incorrectness logic called UNTer. And UNTer stands for non-termination, under-approximate non-termination logic. Where we combined the incorrectness logic rules with the divergence rules to be able to build, analyze very large programs that have potentially infinite loops, cyclic go-tos, et cetera, et cetera. So how does that look like? We introduce those new triples called divergence triples. And the way they read is that if you execute a piece of code C that starts in a pre-state satisfying P, well, then C diverge, right? So if you execute C in a precondition P, then C diverge. Or C as a divergent trace starting from P. That, for example, represent, graphically speaking, a trace that never terminates, that goes from S to S1 to S2, and that goes infinitely like that. We have a bunch of divergence proof rules in our logic. For example, conditionals, where you start, if you assume that P and B C1 diverge, if C1 diverge starting in P and B precondition, then if B, C1, else C2 diverge starting in P. Similarly, if you know that C2 diverge when you start from a pre-state satisfying P and not B, then if B, C1, else C2 diverge when it starts in P. Similarly, those divergence rules handle loops just fine. If you have a piece of code C that goes from P and B to P and B, then you know that if you put that piece of code C into a loop while B, then while B, C, starting in a pre-state, satisfying P and B diverge. This is what we call a lasso property. You can imagine like a very large state space in a graph. And in fact, if imagine a cowboy lasso feature in that state space where you basically come back on an existing state that you've seen before, and you only need to analyze a finite prefix of a trace to determine that this particular path is not going to terminate. We have another while divergence rule where if you have a piece of code C that starts, if starting in a pre-state satisfying P and B diverge, then you know that while B, C will diverge if it starts in P. We can also handle sequential composition just fine. If you have a piece of code C1 that goes from P to Q, and another piece of code C2 that goes from Q and diverge, then you know that the sequential composition on C1 and C2 diverge. Similarly, you can have short-circuiting in divergence analysis, where if you have a piece of code C1 that goes starting in P diverge, then you know that the sequence of C1 and C2 will diverge when starting in P. It's great. It's beautiful. We have a soundness and completeness result for this logic. But not only that, we built a tool. We actually implemented this in the Infer framework from Meta, and particularly we extended the pulse checker to be able to find non-termination bugs. We've also combined the Hunter logic with separation logic for compositional analysis. And this tool is open source. You can check it out at GitHub, on github.com. And we found a number of different divergence bugs in real projects. We've got the reusable badge at OOPSLA. And we're working with the Meta folks to extend the tool and integrate possibly. Our results, we found a bunch of real bugs in a bunch of real programs. As far as we know, we are the first tool that can handle very large programs for non-termination analysis. I want to attract your attention not only on the bugs found, but also how fast that tool actually is. In order to analyze OpenSSL, we need 1.5 minutes to analyze 800,000 lines of code, thanks to the path dropping and the K-bounded analysis that we've implemented. A few examples of bugs we found, for example, in OpenSSL. If you look at the OCSP responder implementation, you see loops like that, where the user actually fully controls what comes on this I/O, and the loop will never terminate if the user data keeps coming in. There are only two loop breaking logic at line 6 and line 9, but this only depends on whether you receive nothing or whether that value actually didn't contain a colon character, which is fully user controlled. We've also found a bunch of bugs in the CryptoPP C++ cryptographic engine. For example, that engine actually wraps the malloc calls. And what it does is that as long as we all know, when malloc fails, it will return a null pointer. So if you keep trying, you will maybe eventually get some properly allocated memory. However, the CryptoPP package do not enforce an upper bound on how many times you're going to retry. You can fix this bug very easily by introducing a number of maximum count. Thank you very much, and I'll take your questions.
Any questions?
Hey, very nice, very elegant work. So looking at your rule for while loops, the one that says that you start from true and you end with true. And so imagine that I am in a concurrent library and I have something like a spin lock implementation, which would satisfy this rule. That would probably be a false positive because it assumes that there is concurrently someone who will eventually going to unlock it. You will probably need some fairness for that. So can you comment on that? So what do we do about that?
Great point. We do not handle concurrency in this logic right now. However, one could imagine an extension of the logic in handling concurrency.
Okay, thanks.
Hi, very nice talk. I have a question. The proving non-termination paper that I knew before this one was from Popple 2008 by Tom Hensinger and Rupak Majumdar and so on. They did not do logic, so it's clearly something new is going on. But in terms of sort of expressive power or something, what's the relationship between their work and your work?
So because we use separation logic, we are compositional.
Right.
Like no previous work combines separation logic with non-termination, as far as we know. So this allows us to actually handle real programs that are extremely large. We're talking million lines of code program. Every other tool that we've tried was not able to handle things that didn't have a main function. So that's the first point. Of course, the logic allows us to be more systematic about it, so we do not need any special encoding. As long as we have the implementation follow the program logic, we don't need to reason about arithmetic or anything like that. And I know, for example, Popple, Gupta, Popple 08, I believe, were all about recurring sets, encoding in arithmetic.
Yeah.
So it's related work, certainly. but we brought it to the next level.
Okay, so the compositionality is very important in your work.
Absolutely.
Yeah, very good, thank you.
Hi, very nice talk. So my question is about lassos. So to the best of my knowledge, most of these works on non-termination that search for a non-terminating lasso find a periodic non-terminating lasso. So the cycle is always of the same length. But it seems to me that you're able to find a witness which does not need to be periodic. So it's also able to detect aperiodic lassos.
Right, so we able, first of all, if you look at the paper, our rule is not that we find the same state, is that we find a state that is a substate of a state we've already seen. That's a slight difference. Also, we only need to find a lasso in one path, right? Not necessarily, not every path, in order to have a non-terminating program, not every path have to diverge, only one path. That's a big difference between previous work and what we've done.
All right.
Am I answering your question?
Yeah. Okay. Thanks.
So I have two questions. One is, I think what you just said. So you're not just doing under-approximated reasoning. You're doing a combination of under and over-approximation. Because you mentioned you want a sub-state to be reachable, not the entire state to be reachable, right? When you look for lassos.
So we actually only do under-approximation, but by sub-state, I mean that not every variable of the state have to be taken into account. In particular, only the variables appearing in control predicates should be are sufficient to induce non-termination.
So you're just projecting out some things, and then you do incorrectness reasoning. Like you do, okay.
That's right.
And so the other part I understand, like, I got the compositional part, like how it all pieces together, but I missed the atom part. Like, what is the initial step that triggers the non-termination analysis? Like, what is step 0? Like, I see how everything propagates beautifully, but like, how do you find the first clue of non-termination?
Right. So it all boils down to this lasso property here, right? So if you, for example, execute a piece of code that you see is not making any progress, it's not necessarily a divergence bug in itself. That piece of code needs to be part of a recurring execution. So whether that's a recursive function, or it's a cyclic go-to loop, or it's a loop that itself is not making any progress, that is necessary to have a real divergence bug. So for example, if you, the most basic example, if you do go-to to yourself, right, that would lead to a divergence bug.
Hi, thank you for the nice talk. I'm a bit puzzled by the second while loop rule for the divergence. Why don't you need that the initial state satisfies B? Because otherwise I couldn't skip the while loop in total, right?
That's right. Well, so if it's not actually satisfying B, you're never going to enter the loop, so there's no divergence.
Yeah, but you have to, right?
Well,
for the second rule down there, I mean, it says, yeah, if you satisfy P.
Say you remove B in P and B, if you have C diverge starting in P, then nothing guarantees you that you will enter the loop.
Yes.
So you need this extra piece of information to know that this loop will be entered, and therefore there will be a recurring state leading to a divergence.
Yeah, but here you say you don't need it, right?
I'm sorry?
Here you say you don't need it, or I think I'm a bit puzzled.
It's like under-approximate, so believing that there exists the possibility of divergence from P. But it doesn't say that if you start from a state
Yeah, I see. Okay,
Yeah.
Thank you.
Here's another way to think about it. You can actually infer that the entire program will diverge. It will diverge. So if this particular divergent piece of code into the bigger program context, then you can prove that the bigger program will diverge, not just that small piece of code.
Hello, I have a small question.
Sorry, I think we need to continue here, so
okay.
let's
Thank you very much.
take remaining questions in the break.
Questions in the hallway.
Thanks.